All right, we have code now, which has an Earth and a moon. It has a craft. The craft feels gravitational forces from both the Earth and the moon. And we can launch the craft in a way we can get fairly close to the moon's surface. You can play with this and find out how to launch the craft so that you can land on the moon, on the back of the moon, on the front of the moon, loop around the moon and land back to the Earth, kind of Apollo 13 style. There is a complication, though, that we have not even begun to consider, and that's that the moon, as we've done it so far, is stationary in space, but the moon actually would be moving in orbit around the Earth. So I'd like to now move the moon. To do that, the moon is going to be its own object in our system, which means it's going to experience forces and react to them. So we have these two sections. This is all about forces on the craft resulting in acceleration, and this is all about the acceleration of the craft changing its position. So this is all about the craft. So I'm going to set this section aside and call it motion of the craft. And then I need to add in an entirely new section, which is all about the moon. So motion of the moon. Okay, it's going to have the same sorts of pieces. Right here, we'll have forces that result in accelerations. And we'll also have kinematics. Okay, those forces. Let's see. There must be a force of gravity caused by the Earth on the moon. Now, I am reusing this variable name here, which you can have complicated feelings about. That's okay. You can change it to something else if you like. It will overwrite whatever is up here, but that's okay because this was used at this point to find f net, and we can use that variable for something else down here, and it'll be overwritten as the program runs through the code a second time. So I'm paralleling this line that we have for f Earth grav back in the craft section. And I know it's going to be, let's see, the moon mass, which I do have defined above, times the Earth mass, and then divided by the magnitude of the vector that points between the Earth and the moon. And I haven't defined that yet. So up here we can have Earth moon, and we'll set that equal to the Earth position minus the moon position. So now we have that vector defined. We can call it here as our Earth moon and square it, and then multiply it by the norm of that vector, our Earth moon. Oh, extra O. Alright, so that is the same as this line right here, but done in the context of the Earth pulling on the moon. Alright, there is actually a force of the craft on the moon, a gravitational force, but that's going to be so small since the craft is so tiny that that can safely be considered negligible. So then the net force on the moon is just the force of gravity from the Earth. Once we find that, we can set the acceleration of the moon. I'm going to call this A moon to distinguish it from up above. And it would be F net divided by the moon mass. Okay, so that finds the force of gravity on the moon and uses that to find the acceleration of the moon as it moves. We need to use that acceleration to update the position and the velocity of the moon. So here I'm just paralleling these two lines about the craft kinematics. So the moon position, moon.pos, is going to equal whatever it was before, the original position of the moon at the previous time step, times the velocity of the moon, times the time step, delta t, plus 1/2 acceleration times time, a moon times delta t squared. Okay, so that will update the position of the moon. And then we can update the moon's velocity as well, so v moon is equal to whatever it was previously plus the acceleration of the moon times the time step delta t. Okay. That's looking pretty good. The moon exists. The moon now has gravitational forces acting on it. It will accelerate in response to those forces. And let's see what happens if we run the program. Unexpected error. Oh, that's a different one. Token operator. Okay, I use the _2, which is just not the appropriate syntax for this at all. So that, here's where that happened. That needs to be asterisk, asterisk. And now I have the velocity of the moon is undefined. Well, if you look at the code, it does say right here that the velocity of the moon is defined right here on this line. But that line also calls the velocity of the moon. So I need to have this initialized somewhere outside, so there's a starting value to work with. Let me just put in this note while I'm here. Update the velocity of the moon. Okay, so I'll go back up here outside the loop where I define initial conditions, and I need vMoon, and it needs to be a vector. So let's see. To begin with, let's just call that 0, 0, 0. We'll think about setting that velocity in just a little bit. Set the initial velocity of the moon. This one here, incidentally, was craft. Okay. Okay, code's working, and look, the moon started falling towards the Earth. That's pretty fun, I have to say. I kind of want to run the code a little bit longer. Let's go for, let's see, we had 1 day. Let's try 3 days and see if that's enough time for the moon to crash into the Earth if it's dropped from rest. Oh, not quite. So actually, if the moon just stopped moving, stopped orbiting, it looks like we would have a few days. Let me go for a month, and I think we'll probably see disaster strike. Our craft has escaped safely from the Earth. The moon is now crashing. We don't have a crash condition set, so it just traveled right through the center of the Earth, which actually might be kind of physical. All right, while the moon is crashing into the Earth, I want to do a little bit of code cleanup. It's always a good time for that. I'm not using my variables in parallel here, which as a coder kind of bothers me. So I do want to, since I've added a new velocity, I want to retro name this one vcraft. So now I have vcraft and vmoon clearly specified. Now when I do that, I'm going to have to change every instance where the velocity of the craft showed up in the code. So I do see it here. While we're at it, let's update this so this becomes a craft, the acceleration of the craft. So that I'll have to update in the code here. Let's see, a couple other instances. One more here. Let's see, have I missed any? Here's another place it shows up in the velocity vector. I'm also noticing I haven't seen these velocity vectors showing up, and I think they're just too small to appear. So I'm going to try making them quite a bit bigger. We'll also do this 1, 2, 3, 4, 5. So let's try 1e6 on each of those, just to see what they look like. Okay, that is actually a little bit big for that velocity vector. That was fun. That was the green vector. Green vector was velocity vector. So, oh, we made the axis right. Let's try a couple orders of magnitude smaller. There we go. Now we can see that velocity vector. Force vector is still not showing up because, what do we do with it? We gave it an axis equal to fnet. Fnet should be okay. Let's try making that a bit bigger then. And I might be seeing it towards the start of the program. Let me just go back to a day. Let's slow down the rate by a factor of 10 so the code just executes a little more slowly. There's that velocity vector. Fun. I still don't see the force vector. Alright, we'll try boosting it up by 3 orders of magnitude. Okay, we may have that be a puzzle to solve in a little bit. For now, I want to start thinking about actually moving the moon. So right now it's falling towards the Earth, and that's not how it actually happens. That would be disastrous. But the moon has some tangential velocity, and so it stays in orbit about the Earth. Alright, so the moon has some velocity tangent to the path. Since the moon is set to the right of the Earth in the positive x direction, tangential velocity would be in the y dimension here. So I'm going to add something here in just a minute. To think about what that velocity would be, I do know things about the moon. I know that it is this far from the Earth, so it has an orbital radius of about 384 million meters. I know that takes about 28 days to travel all the way around. So I can do that math. It's not so hard to figure out how fast it must be moving, and it's right about 1,000 meters per second. About 2,000 miles per hour. I also would like to see the moon's motion, so I'm going to make a trail for the moon. Make trail equals true. And since the trails tend to be a little bit big, we'll go moon trail radius. I'm going to set it equal to about twice the width of the craft trail radius, since the moon is quite a bit bigger anyways. All right, let's see what happens. There we go. The moon is moving. the craft is approaching the moon, but by the time it reaches where the moon was, the moon is no longer there, and the craft does not feel those forces from the moon. So if you're working at NASA and you want to land at the moon, you've got to adjust your launch trajectory so that you arrive at the moon where the moon is going to be when you arrive at that spot, and that's tricky. So the last thing I'd like to do in this video is troubleshoot that force vector that we're supposed to be seeing acting on the craft. I think I have some sense of what might be happening. Here I noticed that we have FNet defined here for the craft, and then we've redefined it here for the moon. So there's a little bit of confusion. The program's not confused, but I am as the coder. So down here when we output FNet, we're actually pulling FNet from the previous definition, which is the force of the Earth on the moon. Just to get a sense of how big that is, I can output that number. I can use my plot as a diagnostic tool. So I'm going to plot, instead of craft position, I'm going to plot FNet. And I have to pick an X, Y, or Z component. Since the craft is launched to the right, the X components can be pretty significant. Z would be a problem because that's out of plane and that is expected to be 0. But this way I can get a sense of how big that force is. So if I look down here, I can see that that force is on the order of 10 to the 17th or 10 to the 18th newtons. That's the force between the Earth and the moon, and that's pretty huge because those masses are so big. I'm not quite sure why that's not outputting. I think probably it's just too large to show, and we're running into some sort of error with VPython. But it's not the force I want to show anyways. What I actually want is the force of the craft on the, the Earth on the craft. And so I'm going to have to be careful with my variables here. So where I call this FNet, I'll call it now FNet craft to be more specific, which means I need that here as well. And then here I can let this be FNet moon, and now FNet moon. Alright, so then I'll have to choose which net force I want to show. I do want FNet craft. I think now this is going to be pretty small. We could try this out. Let's do FNet craft just to get a sense of the magnitude. I still don't see the arrow. Here I see those forces on the order of, a few hundred newtons. Much, much, much smaller. So I'm going to have to boost that up so that we can see it. I'm going to try, what is that, 1E5. We'll see how that does. Yeah, and now I can see it. There's that force vector quite large from the Earth and then vanishes to almost nothing. If we look in our plot, we can see that growth of the force vector and then diminishing as we travel through that interstellar space, interplanetary space, whatever you want to call it, between the Earth and the Moon.